All right, so here's the third problem on the second half of the review. This one involves a lot of smaller parts, but a lot of times you like that because each part will give you a chance to earn some points. If you miss part of it, you're not stuck missing all of it. So in this case, there's a stunt car that starts from rest at a stop sign, accelerates for 50 meters, gets to 17 meters per second, lets off the gas, and coasts over a hill. And you want to find out, are they going to make it over the hill without flying off of it? They don't want that to happen, or maybe they've decided they want to see if that's fast enough to make it go flying off the hill if it's a really good stunt. But they give you some information about the hill, that along its top it's kind of circular with a radius of 20 meters, and the height of the hill above the road is 8 meters. So looking at that, reading through the problem, there's a lot of stuff about kinematics because it asks for acceleration, it asks for time. You have initial velocity, distance, and final velocity, so those are going to come up there. You have several equations there. Then it asks for the net force. So you have to be careful when it says magnitude of the net force or magnitude of anything. Remember, magnitude is just part of the vector. It's the number and the units, not the direction. So thinking back to vector from Despicable Me, for those of you who are big Despicable Me fans like all of us are. Then the net force is mass times acceleration. Circular motion, because of it's going along the hill, we need to include circular motion. And then for the last part, because it's going at a certain speed and you know how fast it's going at its height at a given point, if you're looking for how fast it's going somewhere else on its path, that's usually the type of thing where we can use conservation of energy. And so we'll see that in part F. All right, so in the first one, it's asking you what is the acceleration. We know the initial velocity is 0, the final velocity is 17, the change in position is 50 meters, so I look at the kinematics equations, and the v squared equals v0 squared plus 2a delta x is the one that makes sense to me. I rearrange that, and I get 2.89 meters per second squared. So that works out pretty well. We're able to solve there without too much trouble. Most people who turned it in early got that right without much trouble. Then you take those results, and there are actually a lot of different equations that you can use for part B. But to get to the hill, we find the time. I just use the definition of acceleration, v equals v0 plus at, but you could use any of the other equations as well. But I know 17 minus 0 over 2.89, I get a time of 5.88 seconds. Then, for part C, it just asks, what is the net force? Net force equals mass times acceleration. We know the mass, we know the acceleration, and you can get the force. Then once it's at the top of the hill, you have weight and you have normal force. In this case, though, they aren't equal. There are no other forces because there's no friction, it says. But to follow a circular path, you need a net force pointing toward the center. So in that case, the normal force has to be less than the weight, or it isn't going to be following that circular path. So then we look at it, so the maximum speed that you can have where there's still enough force to keep it in contact, that's where the idea is that if it's about to lose contact, that's at that instant where the normal force goes to 0. It's like when you're jumping. It starts out where there's more normal force than your weight to lift you off the ground, but then right as you're losing contact, the normal force is going back to 0. So that, because it's a circular path, we can say that at that point the net force is only the weight because the normal force has gone to 0, and then we know the acceleration is 9.8. And then if you use the radius and 9.8 to find the velocity, I get 14 meters per second. So then, if I want to be going at 14 meters per second at the top of the hill, I need to figure out how much kinetic energy I'm going to have at the bottom of the hill. So I write out the total energy at the bottom of the hill, which is 1/2 mv squared plus mg times 0. And then at the top of the hill, we have our final velocity, but we also have our 8 meters. And then our final velocity is going to be 14 meters per second. That's what we're trying to find. And the initial velocity, that's what we found in part E. Now the initial velocity is what we're trying to find there. But because in the problem they said there's no frictional losses, that means the energy at the top of the hill has to be equal to the energy at the bottom of the hill. So that means we set those two things equal to each other. And if you notice that mass is in every single step here, so I can just cancel those all out. And I end up solving and I get about 18.8 meters per second. So if you start out going 18.8 meters per second, that's the fastest you can be going at the bottom of the hill and stay in contact. So your stunt where you're going 17 meters per second, you'll definitely be able to stay in contact with the hill all the way across. So that should work.